Hello, everyone, and welcome. I'm Dr. Sudhyendra S.G. Last time, we put together an ALU. You know, the part of a computer that does all the heavy lifting with math. But that brings up a really big question. What's the point of calculating anything if you can't remember the result? That's where memory comes in. And for all you educators and curious minds out there, getting this part is absolutely key to understanding how a computer really ticks. I want you to think about a moment we've all had, that super frustrating one. You're maybe hours deep into a project, or you're just about to beat that final boss in a game. And then the power flickers. And just like that, everything you were just doing, it's gone. Vanished. Why? Why does that happen? Well, that painful moment is brought to you by your computer's short-term memory, also known as RAM. And the thing about RAM is it's what we call volatile. It needs a constant stream of power just to hold on to information. So our goal today is to build our very own memory circuit, right from scratch. We're going to start with the smallest possible piece, a circuit that can remember just one single bit. All right, let's get into it. Now, your first thought might be, hey, can't we just loop a logic gate's output back into its own input? It's a clever idea, right? But it has a huge flaw. If you do that with an OR gate, once you turn it on, it's stuck on forever. And if you try it with an AND gate, once it's off, it's stuck off forever. Neither one can be changed, which, makes them pretty useless for memory. So the solution is to combine them. You put them together into something called an AND OR latch. And this right here, this is the magic piece. This is the fundamental building block of all memory. It's a clever little circuit that you can tell to remember a 1 or a 0, and it will hold on to or latch that value. So how do we actually control this thing? It's surprisingly simple. We have one wire, a set input, that tells it to store a 1. And we have another wire, the reset input, to store a 0. The output just shows whatever we told it last. It latches on to that value. And just like that, seriously, congratulations, you've just built a 1-bit memory cell, conceptually at least. Okay, let's make this a little more practical. Instead of having separate wires for set and reset, we can upgrade to what's called a gated latch. This version has just one data wire for the value, the 0 or the 1, and a super important second wire called write enable. Think of this write enable wire as a switch, or maybe a lock on a door. When it's off, the memory is locked and can't be changed. But when it's on, we can write new data into the latch. All right, storing one single bit is a great start, but let's be honest, it's not very useful by itself. To store something more meaningful, like a number or a letter, we need to group these little latches together. So, by putting 8 of them side by side, we create what's called an 8-bit register. And since 8 bits makes 1 byte, we can now store actual numbers. And this idea of a register, it's actually central to the entire history of computing. You can see the evolution right here. Early processors back in the 70s, they used 8-bit registers. Then they grew to 16-bit, then 32-bit, and today, most of our computers are using 64-bit registers. That means they can work with absolutely massive numbers all in a single go. But here's where we hit a massive, massive wall. Let's say we want to store something small, like just 256 bits. If we tried to wire up each latch individually, well, it would be a complete nightmare. You would need 513 separate wires just to manage it. That is totally, completely impractical. There's gotta be a better way. And of course, there is. The solution is just elegant. Instead of thinking of our latches as one long line, we arrange them in a 2-dimensional grid, a matrix. The best way to picture it is just like a city map, with streets running in rows and columns. And here's the genius part about this grid. To pick one single specific latch out of thousands, all we have to do is activate its row wire and its column wire. And boom, only the memory cell sitting at that one single intersection gets selected. It's a brilliantly efficient system for pinpointing any bit we want. This grid system gives rise to one of the most fundamental concepts in computing, the memory address. It works exactly like a street address for a house. It tells the computer the precise location of any memory cell. We just combine the binary code for the row and the binary code for the column, and that creates one unique address for every single bit. Okay, so we can pick one bit, but usually we work with bytes, right? We want all 8 bits at once. So how do we do that? It's simple, really. We just stack our grids. We use 8 of these grids in parallel, 1 for each bit. When the computer calls out a single address, it's actually activating the same row and column on all 8 grids at the exact same time, letting it read or write a full byte all at once. And this is where things get really, really powerful. You see, the number of bits we use for the address itself determines the total amount of memory we can have. An 8-bit address, it can only point to 256 different spots. But jump to a 32-bit address, and suddenly we can access over 4 times billion bytes. That's 4 gigabytes. The growth is just exponential. So what about the 64-bit addresses that we use in pretty much all modern computers? Well, that allows for a theoretical maximum of 1/8 quintillion bytes of RAM. I mean, that number is so ridiculously huge, it's hard to even wrap your head around it. For all practical purposes, it's a nearly unlimited amount of memory space. And that finally brings us to the name. This incredible ability to jump to any address in any order without having to sift through all the ones that come before it, that is precisely why we call it Random Access Memory, RAM. It's the computer's workspace, its short-term memory, holding everything it needs to get the job done right now. So we've really gone on a journey here, haven't we? We started with the simple idea of a single latch that can hold 1 bit, and we've built all the way up to what you actually see inside a computer. A modern stick of RAM is just this grid principle scaled up to an unbelievable degree, with billions and billions of these tiny memory cells packed onto one little board. Now, I should mention, the latch-based memory we built today is called SRAM. It's super fast, but it's also expensive. The main memory in your computer is probably DRAM, which uses a different technology and is much cheaper to make. And then you have things like flash memory in your SSDs and USB drives, which can even remember things without power. The technologies are different, but they all share that same fundamental idea of using addresses to store and find bits. If there's one really important takeaway from all of this, especially for those of you who teach these concepts, it's the idea of abstraction. Computer memory is really like a set of Russian nesting dolls. You start with the tiniest doll, the latch, which stores 1 bit. You put those into grids to make a memory block. You put those blocks onto chips, and you put those chips onto a RAM module. Each layer just builds right on top of the last one. So we've done it. We've built a calculator with our ALU, and now we've given it a memory to store numbers and results. We have the 2 most important pieces of the puzzle right in front of us. So the final big question is, how do we put them together to create something that can actually run a program? How does a computer think? Well, we're going to answer that next time, when we combine our memory and our ALU to build a CPU.